Welcome everyone to this new Gen webinar sponsored by Redshift Bio entitled Next Gen IR Spectroscopy of Protein Structure Perturbed by Pressure. I'm Jeff Pogaliskas, Technical Editor for Gen, and I'll be your moderator for today's presentation. While many researchers tend not to think about physics on a regular basis, for structural biologists and protein chemists, it's an integral part of their existence. In order to have a greater understanding of protein structure and how forces of the physical universe act upon these molecules, scientists in this space have developed some truly innovative techniques. For instance, infrared spectroscopy, circular dichroism spectrophotometry, and fluorescence spectroscopy are popular methods for monitoring changes in protein secondary structure. Yet, each technique has its limitations in measurable sample composition. The next-gen IR technique, Microfluidic Modulation Spectroscopy, or MMS, provides high-resolution structural information that's critical to understanding the effects of protein misfolding and aggregation that can plague biotherapeutic manufacturing. Having the ability to monitor structural changes that can alter the drug during development would be ideal. However, these changes have been historically difficult to detect. Thankfully, MMS can identify and detect these changes with greater sensitivity and accuracy without the need for dilution or chemical alteration. Now let's find out a little bit about our presenters for today's webinar, who will discuss the basics of MMS technology, as well as review pressure-assisted protein refolding and pressure perturbation coupled with MMS to study stability in biopharmaceutical formulations. First, we'll hear from Matthew McGann, who is a field application specialist and marketing manager at Redshift Bio. Mr. McGann is an industry specialist in biopharmaceutical product development, including candidate screening, formulation development, stability assessment, and particle detection technologies. He'll tell us about MMS, how it can be used to measure higher order protein structure, in addition to the advantages of the AQS3 Pro system in assessing secondary structure. After that, we'll hear from Alexander Lazarev, who is Chief Scientific Officer at Pressure Biosciences. Dr. Lazarev heads a multidisciplinary team of researchers who are aimed at promoting the use of hydrostatic pressure as a thermodynamic driver of biochemical processes, as well as tasked to try to eliminate major bottlenecks in biomarker discovery, drug development, manufacturing, and diagnostics. Today, Dr. Lazarev will tell us how he and his team utilize hydrostatic pressure to control protein conformation for structural analysis. Before we begin with Matthew's presentation, I want to remind the audience to stick around for a Q&A session that will happen right after the last talk. Don't be shy, send in those questions, any question you might have. It's really very easy. All you need to do is click the Ask a Question tab on the right-hand side of your screen, type in your question, and hit submit. We'll try to get to as many submitted questions as we can. Okay, for now, let me turn the webinar over to Matthew.
Good morning and welcome to today's webinar presented by Redshift Biosciences and Pressure Biosciences. My name is Matthew McGann and I'm the Field Applications and Marketing Manager at Redshift Bio. Today's webinar is going to be focused on the next generation IR spectroscopy of protein structure perturbed by pressure. And this morning I'm going to introduce to you microfluidic modulation spectroscopy as a tool for measuring higher order structure of proteins in conjunction with pressure perturbation. Measuring protein structure can be a complex task that requires an understanding of many different analytical techniques and a broad understanding of how protein structure, function, and formulation can affect one another. As we know, protein structure can be very sensitive to changes in local environments, such as pH, ionic strength, temperature, and even sample concentration. When working in applications such as formulation and development for biopharmaceuticals, a full understanding of protein structure is really a two-sided coin. On one side, we have the need to fully quantify and measure the structure of a protein itself. And on the other side, we have the need to ensure that structure does not change during manufacturing, processing, fill finish, shipping, and delivery of the sample all the way to the patient. In this talk, I would like to introduce you to the AQS3 Pro, an instrument which is a new generation microfluidic based IR spectrometer with functionality far beyond that of existing technologies. To begin with, I'd like to discuss some of the current limitations of the toolset used for protein assessment. When it comes to biotherapeutic products, there are 4 primary areas of characterization that is generally required by a regulatory body, and these 4 areas would come together to form the fingerprint of a biological molecule. This fingerprint would include quantification or a measure of the concentration, structural information, including secondary and tertiary structural information, stability profile information, including the effect of excipients and additives to the sample, and an aggregation profile covering particles from oligomers to submicron and subvisible particle content. When it comes to quantification, UV-Vis spectrophotometry would be considered the most incumbent technique. We do know that UV-Vis spectrophotometers have quite a limited dynamic range, and it is often necessary to dilute samples in order to measure the concentration accurately. In terms of structural information, measuring secondary structure, circular dichroism would be considered the most incumbent technique. However, circular dichroism does have quite significant limitations, both in terms of the concentration range that it can measure in, which is quite low, and its ability to measure in complex formulations, as it is not really compatible with excipients. In terms of stability, differential scanning calorimetry would be considered the gold standard for understanding the thermodynamic properties of a protein as it undergoes unfolding processes. DSC, however, does not provide higher order structural information. With regard to aggregation, size exclusion chromatography and analytical ultracentrifugation are both methods that can be quite complicated to implement. However, some of them do provide automation in order to complete the measurements. So if we break down protein characterization into the 4 areas of protein structure, we can see that we have a wide and diverse array of tools available to us for characterizing proteins. In relation to protein primary structure, mass spectrometry offers a high throughput technique that allows us to characterize the mass of proteins very rapidly. In terms of tertiary structure, size exclusion chromatography allows us to calculate the molecular weight of our proteins in a very high throughput fashion. Quaternary structure can easily be calculated using techniques like dynamic light scattering, and these techniques are also very high throughput. The issue, however, is in relation to secondary structure. When it comes to measuring secondary structure, we don't have the same level of automation and breadth of tools available. Circular dichroism would be the most incumbent technique used for measuring protein secondary structure. And we know that the concentration range of circular dichroism is quite limited, and its ability to measure samples in complex buffers or with excipients is very limited as well. FTIR, on the other hand, has a better ability to deal with excipients and complex buffer systems, but requires a much higher concentration in order to obtain a good clean signal, and is quite difficult in terms of reproducibility and operator usability. Microfluidic modulation spectroscopy is a new technology which can assess protein secondary structure over a concentration range from about 0.1 mg per mil to over 200 mg per mil, and is compatible with the complex formulations required to manufacture stable biopharmaceutical products. In comparison to the incumbent technologies such as CD, DSC, and FTIR, the system can cover a dynamic range of 4 decades of concentration, which is far beyond the capabilities of these techniques. The AQS3 Pro system is the next generation of instruments to assess protein secondary structure. The system combines 4 key features. Firstly, a high-powered quantum cascade laser, providing significantly brighter light source than a traditional spectrometer. A high-precision microfluidic flow cell, providing a unique microfluidic modulation spectroscopy platform that minimizes background drift and other issues associated with benchtop spectrometers. A fully automated sample handling system, which is compatible with standard microwell plates for easy unattended measurement. And finally, a user-friendly software platform that provides simple setup of measurements and advanced analytical tools that allow you to rapidly determine higher order structure information for easy sample comparison. At the heart of the AQS3 Pro system is the microfluidic flow cell. The microfluidic flow cell, once primed with sample, can rapidly alternate the buffer and sample through the observation zone, providing an easy measure of the differential absorbance between the sample and buffer. Interpolation of these data points can provide a spectrum. The rapid sample buffer referencing technique without moving the cell provides spectral reproducibility of greater than 99%. One of the major features of the AQS3 Pro is its analytics software package that allows you to convert spectra all the way through to higher order structural information with just a few clicks of the mouse button. To highlight this, we're going to go through an example workflow where we've taken an antibody fragment and exposed it to a range of temperatures in order to look at essentially a melting profile of that sample. Before we do that, if we have a look at the lower set of graphs on this screen, you can see that because this is an absorbance-based measurement, it is possible to generate a concentration curve of our samples. And one of the great features of this system is that the measurable concentration range, as I've mentioned, is between 0.1 and 200 mg per mil, and the system shows great linearity across that range. Moving on to the upper workflow on this screen, it's very easy to take this differential absorbance spectra and convert it into higher order structural information, as we'll discuss on the next slide. Now looking at this slide, if we follow the top line of spectral processing, what you can see here is that we've taken the differential absorbance spectrum and converted it to a second derivative in this case. The second derivative is a great way of easily identifying differences in spectra that may not be as obvious in the raw spectrum. Once we have a second derivative, we can then produce what we call a difference spectra. Now this is subtracting each spectrum from a reference spectrum, and it allows you to very quickly highlight the key wave numbers in which significant change is occurring in the sample. Once you know these key wave numbers and can relate them back to structural parameters, it is then possible to generate a stability profile. In this case, we've tracked 3 wave numbers related to beta sheet composition of the sample. Those wave numbers are 1624, 1641, and 1697. And we've also traced an alpha helix parameter at wave number 1654. And what this graph clearly shows is that the structural composition of this sample changes drastically once the sample reaches approximately 65 to 70 degrees. Following the lower path in this software workflow, we can also generate higher order structural information in terms of the fractional content of higher order structure very quickly and easily by taking the second derivative and converting it into an area of overlap plot, which involves inversing the plot and then applying a global baseline. We can very quickly look at the percentage area of overlap between 2 spectra to determine how similar or how different those spectra are to one another on a simple percentage basis. Once we have these spectra, we can then apply some simple models in terms of higher order structure to deconvolute these spectra, which allows us to calculate the fractional contribution of a range of structural parameters such as beta sheet, antiparallel beta sheet, alpha helix, and so forth. In the final plot, what you can see here is that we are graphing the composition of each of these higher order structural features relative to the temperature that the sample has been exposed to. Now, knowing that red represents the highest temperature, you can see that as the sample is exposed to higher temperature, in this case, the amount of anti-parallel beta sheet increases, and conversely, the amount of beta sheet content decreases. Now, this is very typical and expected of an antibody type sample. So to conclude this section of this morning's webinar, I'd like to review some of the key pieces of information relating to the AQS3 Pro. The system provides 5 critical protein quality measurements, those being aggregation, quantitation, stability, similarity, and structure. With the improvements in light source, the system provides a 30 times improvement in sensitivity relative to current conventional infrared systems. It also offers the widest measurable concentration range of any structural analysis platform, measuring from 0.1 mg per mil to greater than 200 mg per mil. With the integrated autosampler, the system provides multi-sample capability and can lead to a 20 times savings in direct labor costs due to the ability to operate the instrument hands-free. Finally, the automated protein analytics tools provided by our software platform directly fulfill the needs of both the operator for simple operation and the scientist for simple data interpretation to take you from your sample to your fully processed data in as short a period of time as possible. I'd now like to hand the webinar over to Alex from Pressure Biosciences, who's going to introduce you to his system and then show some examples of how the AQS3 Pro can be used to observe protein structure under pressure.
Thanks, Matthew. Some really great information and very nice data for the AQS3 system. Before Alexander begins, I want to remind the audience once again to stick around for the Q&A session that's coming up right after his talk. Again, don't be shy. Send in those questions. We'll try to get to as many of them as we can so that we can have a very nice, lively Q&A session. Just type your question into the Ask a Question tab on the right-hand side of your screen and hit Submit. Okay, let's keep things moving and hear what Alexander has to say. Alexander, the floor is yours.
Hello, everyone. I'd like now to switch gears and talk about one of my favorite subjects, thermodynamics. But please don't worry, I have no equations in any of my slides. First, I'd like to start with a couple of citations from a classic 1999 publication by the champions of high-pressure protein refolding, 2 University of Colorado professors, John Carpenter and Theodore Randolph. They said, protein aggregation is subject of intense investigation in disciplines including human medicine, fundamental protein chemistry, and biotechnology. For example, aggregation can have severe consequences in human disease, such as Alzheimer's disease and Parkinson's disease, and in the manufacturing, shipping, storage, and delivery of protein therapeutics. They also said that in spite of recent progress in theoretical and computational approaches to understand protein folding and refolding, efforts to manipulate folding in vitro often are plagued by competing off-pathway aggregation processes. The bottom line of it all is that protein aggregates are highly immunogenic, potentially causing adverse immune reactions and inactivation of biologic therapeutic agents. Understanding and control of protein aggregation can significantly improve our ability to produce better biologics. At Pressure Biosciences, we employ high hydrostatic pressure to control protein conformation. Most pressure effects in biological systems are facilitated by hydration. Proteins undergo unfolding by infusion of water molecules into their hydrophobic core. Such unfolding is typically reversible at moderate levels of pressure. I'd like to stress specifically that the extent of unfolding by pressure is protein-specific and highly reproducible, much unlike entropic thermal denaturation. Pressure allows us to manipulate protein structure with no or minimal addition of chemical or thermal energy. Pressure causes dissociation of multimerical protein complexes. As we apply higher pressure, it leads to unfolding of monomeric proteins, resulting in modulations of protein function. Pressure happens to work in synergy with chemical denaturants. In the next few slides, I'm going to show you a few examples of how pressure can be used in a convenient research settings to study proteins. At the beginning of the 20th century, Harvard University professor Percy Bridgman laid the foundation for today's high-pressure solid-state physics. He also experimented with so-called soft matter, which is the way physicists refer to biological material. He noticed that an egg white could be cooked at room temperature solely by application of high pressure. We have recently repeated this classic experiment in one of our instruments. Pressure levels generally higher than 500 megapascal or 70,000 psi begin to cause irreversible protein denaturation. Longer exposure or higher levels of pressure lead to more rapid and more complete denaturation. Pressure denaturation of proteins is synergistic but very different mechanistically from the thermal denaturation. Thermal energy promotes random movement of protein molecules until the alignment breaks, while pressure actually suppresses Brownian motion and drives every protein molecule to the same conformational state by infusion of water molecules into what normally are solvent inaccessible cavities inside protein structure. Pressure effects were known for more than a century. However, all this time, high-pressure research was confined in the laboratories of a few enthusiasts because there was no commercial equipment available to generate and control very high level of pressure in the life science research settings. Our company has introduced a line of dedicated appliance-like benchtop high-pressure instruments that help to promote high pressure as a convenient research tool. Pictured here is the Barocycler 2320 Extreme, an appliance that controls both temperature and pressure and allows up to 16 samples of up to 150 microliters each to be pressurized in one batch in specialized sample containers. Sophisticated software allows accurate pressure control ranging from continuous pressurization to rapid pulses of pressure from atmospheric to very high level and back to facilitate various biochemical processes, from rapid proteolytic digestion to screening for best chemical environment for protein refolding. We have originally started in the area of biomarker discovery and proteomics by accelerating and improving reproducibility of proteolytic digestion, as I mentioned before. By unfolding protein substrates, pressure helps to expose hidden cleavage sites to the enzyme. Proteases appear to be more resistant to high-pressure denaturation, and several of them, such as chymotrypsin and most notably endoproteinase Lys-C, show remarkable ability to work under pressure like all of us. They actually get significantly accelerated without losing their specificity. In this example, myoglobin as a model system was digested and monitored by disappearance of the parent band on an SDS page gel. Indeed, chemotropic agents and pressure are synergistic. Apparently, pressure makes ordinary organic solvents act as chemotrops too. This is a great news for mass spectrometry community that is generally trying to stay away from any chemical additives in their samples. However, not every enzyme accelerates under pressure. In fact, partial unfolding is more likely to make enzymes less efficient. A yeast lysate was interrogated with the specific chromogenic and fluorogenic substrates to demonstrate the ability of pressure to selectively inactivate various enzymes in their optimized buffers. As you can see here, alanine S-transferase is shown to be the most pressure-labile enzyme, while the alkaline phosphatase is the most robust enzyme with respect to pressure inactivation. Pressure helps to make fast and reproducible protein digest for peptide fingerprinting in biopharmaceutical quality control settings. It also turns out that pressure helps to digest native unreduced monoclonal antibodies and other proteins in order to rapidly and reproducibly characterize location of disulfide bonds. Pressure also helps to accelerate deglycosylation using protein N-glycosidase, abbreviated as PNGF enzyme. In addition to saving significant amount of time, These sample preparation methods carried out in the Barocycler are shown to be extremely reproducible. This slide shows the work published by a Genentech team that reports pressure-enabled fast Lys-C digestion of their monoclonal antibody product, preserving disulfide bonds, minimizing disulfide scrambling, and maximizing quantitative peptide recovery, thus streamlining multiple critical quality attributes analysis. Now let's get back to protein refolding for a moment. About a third of the total volume of protein therapeutics is being produced in bacterial expression systems. Bacteria do not require expensive media components. They grow very fast in traditional stainless steel bioprocess equipment and produce large amounts of recombinant proteins. With rising demand for biosimilars, antibody drug conjugates, and some fusion proteins that cannot even be produced in the eukaryotes, bacterial expression systems are gaining renewed interest again. Research reagent proteins are also produced predominantly in bacterial systems. Usually overexpressed proteins get dumped into a misfolded aggregated state called inclusion bodies. While inclusion bodies contain mainly protein of interest and can be obtained by a few centrifugation steps, thus making purification very easy, the protein must be solubilized and refolded at the end. Turns out that aggregation mechanisms responsible for protein deposition in inclusion bodies and also amyloid fibrils have a lot in common. Studies done by FTIR demonstrate that both types of protein aggregates are rich in anti-parallel beta sheet structures. Both types of aggregates can be selectively disaggregated and solubilized by hydrostatic pressure. Proteins deposited in inclusion bodies must first be unfolded, untangled, and solubilized to its monomeric state. Afterwards, individual molecules are allowed to refold, guided by appropriate chemical environment in the refolding buffer. Very few proteins refold spontaneously after they are solubilized from inclusion bodies. So typically, protein refolding methods rely on very high concentrations of chemical denaturants such as urea or guanidine that must be removed in a lengthy dilution or dialysis steps prior to refolding. At this stage, reaggregation is likely to occur since unfolded proteins are the most susceptible to aggregation. However, if pressure is used to unfold proteins, it could be simply and quickly turned off when appropriate. Therefore, high-pressure refolding could be generally carried out much faster and at a significantly higher concentrations, leading to greater yields of properly folded active proteins of interest. This slide shows the popular energy landscape of protein folding and aggregation diagram. It shows minimal energy states that sometimes correspond to non-native structures such as amorphous aggregates or amyloid fibrils that could perhaps be even more energetically favorable than native protein structures. However, if one applies the pressure to some of these structures, refolding could be carried out. Previous studies have shown that the moderate high pressure of 100 to 300 megapascal is generally effective for the dissociation of protein oligomers and aggregates, while relatively higher pressure is needed to denature native monomeric protein structures. Pressure propagates through media with the speed of sound and affects every molecule in solution to the same extent. Thus, uniform refolding process could be achieved if chemistry surrounding the protein molecules is right. For example, complete solubilization of human proinsulin inclusion bodies occurs in only 5 minutes under pressure, as you can see the photograph on the left. After the pressure is lowered back to atmospheric level in a 2-hour gradual ramp, and in the optimal redox buffer containing 9:1 ratio of cysteine to cysteine, proinsulin monomers refolds to its active state, and insulin precursor protein, as shown on the reverse phase HPLC chromatogram on the right side. Pressure unfolds inclusion bodies very easily. However, protein refolding requires a lot of other parameters to be just right. Optimization of the refolding chemistry requires a series of multivariant screening and experiments designed to determine correct pH, ionic strength, temperature, concentration of other reagents, co-solvents, and affinity binding ligands, if applicable. Pressure Biosciences offer contract service and equipment for optimization of refolding parameters at the customer site. Our flagship product, Barocycler 2320EXT, has a ramp mode option in its software. This feature allows users to slowly ramp the pressure up, holding it for minutes to hours, if necessary, and slowly release pressure at a predefined rate. This feature is exceptionally useful for protein refolding to prevent rapid reaggregation of partially unfolded proteins. By analogy, protein aggregation is another major problem in the biopharmaceutical industry. Protein aggregates tend to be immunogenic, leading to drug inactivation and unwanted adverse reactions in patients. Pressure could be used as a convenient tool for protein disaggregation. From biomanufacturing to formulations, accelerated stability studies can be carried out to determine whether the protein is happy in a specific chemical environment, or it is about to form fibrils or highly immunogenic aggregates. Understanding mechanism of protein aggregation can help to develop formulations that favor protein stability. Unfortunately, there is no universal method to study protein structure in a rapid manner. Here is an incomplete list of complementary tools that help us to tease out structure of the proteins. While NMR, crystallography, and mass spectrometry provide information-rich content, they cannot be used as a screening tool. Therefore, we're always on the lookout for rapid and automated tools to characterize conformational changes in proteins. Moreover, partially unfolded proteins tend to be very sticky. They aggregate, clog HPLC columns, create turbidity that interferes with fluorescence, UV-Vis, and CD spectroscopy, as well as introduce significant errors in laser scattering measurements. Therefore, we turn to the infrared spectroscopy as a tool that is less sensitive to turbidity and scattering, yet as informative as circular dichroism spectroscopy with respect to protein higher order structure. Thanks to our collaborators at Refolding Bio, we recently got to try their AQS3 Pro system, employing a new approach to infrared spectroscopy entitled Microfluidic Modulation Spectroscopy. As Matt showed a few minutes ago, this instrument can qualitatively report changes in protein structure as a function of time or chemical environment with great reproducibility and high sensitivity. So we thought, what about pressure? For our first set of experiments, in order to understand the power of their approach, we selected a well-characterized model, Human IgG, a well-soluble protein that is known for its propensity to aggregate in specific conditions, pH, temperature, and pressure, all known to trigger IgG aggregation. We have compared effects of 4 levels of pressure and 1 heat condition on IgG aggregation in 2 buffers, conventional phosphate buffer saline and PBS containing 10% N-propanol as a co-solvent. The graph on the right shows Bradford protein assay of protein remaining in solution after pressure treatment. It turns out that our favorite N-propanol acts in synergy with pressure, causing efficient unfolding in irreversible protein aggregation at much lower pressure levels compared to PBS alone. After being pressurized to 60,000 psi, we have lost almost half of the protein in the buffer containing N-propanol, while IgG content was totally unaffected in a similar pressure in PBS alone. We had to discard remaining samples treated at 80 degrees Celsius or 90,000 psi that lost most of the protein to a pellet. Remaining samples were analyzed in the Refolding Bio system. Although all proteins remain in solution, the 60,000 psi treatment of IgG in PBS resulted in a significant, about 6.5 to 7% conversion of the parallel beta sheet content into the anti-parallel beta sheet. This conversion is a good indication of initial stages of aggregation. However, thermal treatment at 80 degrees Celsius resulted in no noticeable structural change. Observed changes remained very consistent for 2 days after the treatment. Even much more remarkable changes were observed in samples containing co-solvent. While samples of 3 replicates for every condition were essentially superimposable, each increase in pressure showed pronounced and proportional conversion of the parallel beta sheet into the antiparallel. Moreover, formation of extra alpha helical regions from turns were also observed, consistent with the literature data suggesting that the aliphatic alcohol co-solvents are conducive to formation of extra alpha helical structures. This is another representation of the same data set on the AQS3 platform. Again, a gradual drop in parallel beta sheet and proportional increase in the antiparallel beta sheet, while a gradual decrease in turn signal corresponding to increase in alpha helical structures is shown here. Please note that the 60,000 psi sample has been virtually visibly turbid, yet data was completely unaffected by this fact. I hope that I was able to give you a little hint today that high pressure in combination with a microfluidic modulation spectroscopy platform could serve as a powerful platform for protein refolding optimization and studies of protein stability in formulations development. I'm convinced that AQS3 platform could be a very useful tool in our team's toolbox as we work with partially unfolded and aggregating proteins. In the end, I'd like to thank everyone who worked on this project and made today's presentation possible, as well as Genetic Engineering News team for hosting us today. And most importantly, thank you very much, all of you listeners, for your attention today.
Thanks, Alexander. Some really interesting data and a nice showcase of the MMS technology and AQS3 platform. All right, the Q&A is going to begin very soon, and I just want to remind everyone once again to send in their questions for the panel so we can have a very lively discussion and try to get to as many questions as we can. Simply type your question into the Ask a Question tab on the right-hand side of your screen and hit Submit. It's that simple. Thanks to everyone who sent in their questions already, and since we have a bunch of them ready to go, let's start the Q&A session. Give us just a moment to get everything squared away, and we'll begin the Q&A presently.
All right, guys, so let's get to the questions. Our first question is going to be for Matt. Matt, one of our audience members would like to know if there are any buffers typically found in protein formulations that are incompatible with the MMS. Do you demo the system?
Hi, Jeff. Thanks for that question. I'd like to answer this with a quote from our Chief Technical Officer, Eugene Ma, actually. And he has been quoted as saying that we still have not found a buffer component which causes a problem or is incompatible with our measurements. So, yeah, the simple answer is no. We don't believe that any formulation components that are typically used in biopharmaceuticals will cause issues with our background. It is worth mentioning, however, that the sample does require a matched buffer as a background measurement, so they do have to be the same concentrations. In terms of demoing the systems, absolutely. We have multiple demo systems available across the US and even across Europe, depending on which continent you're on, and multiple teams around the world that can help with demoing those systems.
Great, thanks, Matt. Alex, a question for you. Can you comment on why you chose Human IgG as a model for testing the synergy between pressure perturbation and MMS analysis?
Well, thanks, Jeff. Most of the biopharmaceutical products in development at the moment are one way or the other monoclonal antibodies. It's a very popular subject. Both of our teams are quite familiar with the IgG. IgG is the inexpensive model that closely resembles individual monoclonal antibodies in terms of their biophysical behavior. And once we actually demonstrated the perturbation and ability to detect those in a very reproducible manner, we certainly will continue to explore other proteins.
All right, great. Thanks, Alex. Matt, another question for you. How much optimization of parameters is needed before measuring each sample or spectrum, and for each sample set?
Okay, so in terms of preparing a sample to go into the instrument, the operator is really required to load the samples into the micro well plate and degas them. And interestingly, the degasser is actually included inside our instrument, so you don't even need an external device for that. Once the sample has been degassed and placed inside the instrument, the software goes through its own optimization procedure for each of the samples that it loads in. For example, it goes through a pressure test which measures the viscosity of each sample so that it can optimize the flow rate for each of those samples independent of one another. So in terms of optimization of parameters, the software does the optimization itself and requires very little, if any, interaction from the user to achieve good reproducible measurements on quite a wide variety of samples.
Great, thanks, Matt. Alex, back to you. An audience member would like to know, what makes you think that there is a strong synergy between the two instrument platforms?
Yeah, we use pressure perturbation every day, and we know that pressure selectively affects hydrophobic interactions that determine protein conformation. In this short trial experiment, we were just kicking tires, how the two platforms work together. The MMS platform really well demonstrated its promise to directly report on the structural changes caused by synergistic impact of pressure and chemistry. So we will definitely continue to develop analytical approaches to take full advantage of the synergy between the PBI and Redshift platforms. I'm convinced that this platform will make our protein refolding services in our group much more efficient.
Great, thanks, Alex. Matt, what are the upper and lower protein concentration limits for this technology?
Okay, Jeff, I guess there's two ways to answer this question, and that is to discuss either the measurable range or the range in which we can observe good higher order structural information. So the measurable range in terms of concentration is about 5 decades, from 0.01 to 200 milligrams per mil or above. In terms of detecting higher order structure and getting clean, consistent, and high quality repeatable spectra, we recommend a concentration range of 0.1 to 200 mg per mil.
All right, great, thank you. Alex, what is the max pressure of the system?
That's an excellent question. The system we featured in this presentation, the Barocycler 2320 EXT, is limited to 60,000 psi, otherwise 400 megapascal or 4,000 atmospheres. Sorry for the confusion in the pressure measurement units. This is actually causing a lot of trouble. But we do have other systems that go to 100,000 psi or 700 megapascal.
Excellent. Matt, here's a long, detailed question for you, but an audience member asks, in a complex sample, i.e. cell extract, or even in plasmid high expression systems, is it possible to analyze protein structure? For example, if I want to compare the structure between two variants using mammalian expression system, can I use this system to analyze the secondary structure?
Okay, so yeah, this is a little bit of a complex sample beyond what we would call a complex formulation. So I guess the best way to answer this is to explain how the instrument requires the sample and buffer composition to be. The buffer that is matched to each sample as it is measured needs to be matched in its components exactly. So, from a pharmaceutical standpoint, the term placebo, i.e. the sample with no active drug component in it, would be the description used. If you're looking at a cell extract, I guess the challenge is going to be that you won't be able to manufacture or produce a background or reference buffer that has exactly the same composition of cell debris, I guess is what you'd call it. So it would be a challenging measurement. If you could remove the cell debris and just isolate the sample down to its protein components, then we probably could do a measurement. But I think it's the cell debris that would be causing a problem in that case.
Great, thank you. Alex, question for you. In one of your slides, you showed a multi-cell holder. How many samples can you process in your pressure system at one time?
That's a great question. Again, the system that they featured today is our smallest analytical scale platform that offers 16 positions for 150 microliter sample containers. Since the pressure is contained in the pressure vessel, one could use the larger container to, let's say, put one sample of about 3 milliliters in size. Our other benchtop product line called Hub Explorer can accommodate 48 samples of the 150 microliter type. Note you can also use larger sample containers, about 10 mils per tube, which will actually, 3 of them which will fit in the Explorer platform. For protein refolding process development, we also have equipment with pilot scale pressure chambers up to 10 liters in volume. And scale up is available to the manufacturing scale with industrial high pressure vendors, our partners, that offer systems with pressure vessels up to 800 liters in size.
All right, great. Thanks, Alex. And stay with me because we got one more question for you. Are you concerned about changes in pH at higher pressure using PBS buffer, which may also affect irreversible unfolding and changes in HOS?
That's a fantastic question. Very few people actually know about it, although it's been published years ago. It's an interesting thing to see that actually people are interested in pressure. Thank you very much. Yes, we are aware of that fact, and in fact, we now launching a user-friendly optical cell that would actually fit in most of the spectrophotometer platforms. And using carefully selected pH indicator dyes, we could measure the pressure changes directly in the pressure vessel. And in fact, PBS does change the pH to almost as high as 1 unit off. There are buffers that do not really get affected by high pressure. For instance, ammonium bicarbonate, we saw practically no pH change in that case. This is just the first time we tried to see if there is any difference, but obviously we'll continue to investigate and take into account the pH changes and so forth. Thank you.
All right, great. Thanks, gentlemen. And with that, we've come to the end of our webinar. So I'd like to remind everyone that the webinar will be archived on the GEN website for up to a year at www.genengnews.com. So if you missed any parts of it, you can watch it again, or feel free to forward the link to any of your friends or colleagues, which we always recommend. I'd like to thank Alex and Matt again for their very informative presentations, and I'd like to thank you, the audience, for your attention and very thoughtful questions. And a very special thanks to Redshift Bio for sponsoring this webinar. Don't forget to keep an eye out for more GEN webinars coming up in the near future. Goodbye for now.